Light and the spectrum.
Section A, the basics.
Light is part electricity and part magnetism, and it travels like a wave. All waves, waves of water, waves of sound, waves of light, waves of whatever, have wavelengths and frequency. Because light travels like a wave, we can measure the wavelength and frequency of light.
Wavelength is the distance from one peak of a light wave to the next.
Frequency is the number of wavelengths that go by a certain point in 1 second.
When you multiply the wavelength of a light wave by the frequency of the same wave, you'll come up with c, the speed of light. C is a constant. Since c is a constant, wavelength and frequency have an inverse relationship. If wavelength increases, then frequency decreases, and vice versa.
The speed of light is always 300,000 kilometers per second, no matter where you are or who you are.
If you don't believe us, consult Genesis chapter 1, verses 19 through 24. And God said, "Let there be light, which travels no faster than 300,000 kilometers per second." And it was good.
We measure light waves in units called nanometers, which are really, really small. How small are they? Well, about a billionth of a meter. A violet light wave is about as long as a bacteria. How small is that? Well, I don't know, but it's really stinking small.
Section B, Planck's law.
Although light moves like a wave, it interacts like a particle. That means that when light hits something, it acts like a little packet of energy. We call that packet of energy a photon.
Each photon carries a certain amount of energy. We can determine the amount of energy a photon carries by determining the frequency of the light. Higher frequency light has more energy.
A guy named Planck came up with an equation that describes the relationship between frequency of light and its energy. It looks like this. Energy equals frequency, or F, times h. What's h? That's Planck's constant. It's equal to 6.63 times 10 to the negative 34th joule seconds. The unit, joule seconds, doesn't really mean anything to those of us who aren't physicists, but you have to have it to make the algebra work out.
So let's say you had some light with the frequency of 10 to the 15th per second. 10 to the 15th what per second? Well, cycles, but they aren't really a unit we measure per se. So we just say 10 to the 15th per second and leave out the cycles, and everything works out in the end, especially the units for energy, which are joules. So you have light with a frequency of 10 to the 15th. What's the energy of one of its photons?
We'll use Planck's equation. E, energy, equals h, Planck's constant, times F, frequency.
So we have energy, E, equal to Planck's constant, 6.63 times 10 to the negative 34th joule seconds, times frequency, 10 to the 15th per second. Whip out your calculators, friends, and multiply.
E now equals 6.63 times 10 to the negative 19. Remember how we said you need joule seconds to make the algebra work out? Well, here's where it happens. If we cancel out the seconds in joule seconds and the seconds down here from the frequency, we're left with joules, which is the proper unit for energy. There, energy of one of those little photons is 6.63 times 10 to the negative 19 joules.
To give you an idea of how little energy that is, eating one pretzel gives you about 40,000 joules of energy.
Now let's see how much energy is in light with higher frequency, say 10 to the 17th per second. 6.63 times 10 to the negative 34th joule seconds times 10 to the 17th per second equals 6.63 times 10 to the negative 17th joules. A little more energy than the other photon, but still, not a whole lot. Individual photons don't carry a lot of energy themselves, but when a whole lot of them get together, like in a laser beam, look out.
This whole rule is pretty intuitive. A light wave that has a higher frequency squiggles back and forth more than a light wave with a lower frequency. The higher frequency wave moves more. Doesn't it make sense that a wave that does more movement has more energy?
Section C, other properties of light.
Light comes in many different flavors, which we identify by their wavelength. All of the wavelengths we can detect make up what we call the spectrum. Some of the wavelengths can be hundreds of meters long, and some of the smallest wavelengths are smaller than the size of an atom.
We can only see the part of the spectrum in the wavelengths between 400 and 700 nanometers. We call this range visible light. Makes sense, doesn't it? Visible light is all the light in the Roy G. Biv rainbow.
Roy G. Biv.
But there's a lot more light out there radiating around us than just our familiar visible light.
The entire spectrum starts with gamma rays, which have the most energy and the smallest wavelength. Then, going down in energy, we have X-rays, ultraviolet light, visible light, infrared, microwaves, and finally, radio.
Gamma rays have the highest frequency of all light, and so their wavelength is really small. But remember what we said about frequency. Higher frequency waves have more energy. Gamma waves are so small and have so much energy, they can bust through just about anything. Whee!
Ultraviolet rays are the ones that cause sunburn. Luckily, we still have enough of an ozone layer on the Earth to prevent the ultraviolet rays from cooking us. Infrared light is heat radiation, and radio waves include TV transmissions and AM and FM broadcasts.
One last thing you should know about light. Light is sometimes called radiation. So if we say infrared radiation, we mean infrared light.
Let's review. Light is energy that moves like a wave and interacts like a particle. A particle of light is called a photon. The speed of light always stays the same, 300,000 kilometers per second. The frequency of light multiplied by its wavelength will always equal the speed of light. To find the amount of energy in one photon, you use Planck's equation, which is energy equals Planck's constant times frequency. Higher energy light has higher frequency and shorter wavelength. Lower energy light has lower frequency and longer wavelength. The full range of light is called the spectrum.
Section D. Wien's law.
Just like the sun, you are emitting light right now. No, not that kind of light. Your body produces heat, right? Well, that's infrared light. If you were to put on infrared spy goggles, you would be able to see how bright you really are.
You and the sun radiate different kinds of light because you and the sun are different temperatures. Everything radiates a little bit of every kind of light. You radiate mostly infrared, but you're also giving off a little bit of radio radiation as well. An object's temperature determines where in the spectrum that object radiates most of its light. Wien's law connects the temperature of a hot body and the wavelength of the brightest light it gives off.
Wien's law says that as an object increases in temperature, the average wavelength of the light it emits becomes shorter and shorter. That makes sense, doesn't it? If we can imagine that everything emits light, then things that have more energy and thus a higher temperature will emit light with higher energy. And remember, higher energy light has higher frequency and shorter wavelength. Wien's law helps us determine which wavelength an object emits most of its light in. If you know an object's temperature, you can use that to determine the wavelength of the light it's emitting. According to Wien's law, the wavelength of emitted light, lambda, is equal to 0.0029 over T, the temperature of the object in kelvins. So let's try one.
We'll use a nearby star that we're really familiar with, which has a temperature of about 5,800 kelvins. This star emits light all over the spectrum, but we want to know in which wavelength it gives off the most light. Let's use Wien's law to find out.
Wien's law says that lambda, the wavelength of emitted light, is equal to 0.0029 meters over the temperature of the light source. The temperature of our star is 5,800 kelvins. Plug that into the equation.
Lambda equals 0.0029 over 5,800. Punch that into the calculator, and we get 5 times 10 to the negative 7th meters. Our answer is in meters, which is okay, but nanometers is an easier measurement for wavelength. 1 meter equals 10 to the 9th nanometers. To convert meters to nanometers, multiply 5 times 10 to the negative 7th meters by 1 nanometer over 10 to the negative 9th meters. Meters cancel out, so now our answer is 500 nanometers. Final answer, 500 nanometers. If you can hear that shuffling in the background, we're getting out a little spectrum sheet, and we see the wavelength of 500 nanometers corresponds to yellowy white light, just like the sun. So, guess which star we were talking about? The sun! Oh, you knew that the whole time, didn't you?
Section E. Stephan's law.
Related to Wien's law is Stephan's law. Loosely, Stephan's law states that the hotter an object is, the brighter it is.
We can illustrate both Stefan's and Wien's law on a graph.
Temperature goes up on the vertical or y-axis, and the wavelength increases right to left along the horizontal or x-axis. As the peak temperature increases, the peak wavelength shifts to the right from the infrared to blue and ultraviolet. The chunk of stuff that peaks at 600 kelvins has light that peaks in the infrared, while the star with a peak temperature of 60,000 kelvins peaks well into the ultraviolet spectrum. This part of the graph illustrates Wien's law. As the temperature increases, the wavelength decreases, just like Wien said.
The area underneath the curve is just as important as where it peaks. As the temperature increases, the area under the curve increases also. The area corresponds to how much energy is released, or the intensity. So we see, as temperature increases, so does intensity, which is just what Stefan said. Intensity, or brightness, increases with temperature to the fourth power. So, according to Stefan's law, if your temperature doubled, then your radiation would increase 16 times.
One more set of light laws to go.
Section F. Kirchhoff's laws.
Kirchhoff's laws help us identify elements by examining the light that they produce. To understand how it works, we have to start where Kirchhoff did.
Kirchhoff noticed something funny about elements and spectra.
Kirchhoff noticed that there are three different kinds of spectra: continuous, emission, and absorption.
If you use a prism to look at a light source directly, you'll see a continuous spectrum. See? Rainbow. A continuous spectrum is that smooth spectrum of all the Roy G. Biv light.
Roy G. Biv.
If the light passes through a cloud of cold gas along the way, the gas will absorb some of the light, and you'll see an absorption spectrum. Absorption spectra look like this, with big black lines. The light that is absorbed leaves the black lines in the spectrum. Absorption spectra are continuous spectra with missing wavelengths. If you look at a cloud of gas that's hot enough to emit its own light, you'll see an emission spectrum. The cloud of gas emits colored light, so you know it's only emitting some wavelengths and not others. The emission spectrum shows bright lines like this. Emission spectra show only a few wavelengths and none of the others.
Why are there absorption and emission spectra? What are those goofy gases doing to mess up the continuous spectrum of light?
It's kind of complicated, but we can explain it simply. The structures of the individual elements makes them absorb some wavelengths of light and ignore others. When the element is cold, it absorbs the wavelengths. Then, when the element gets hot enough to emit its own light, that same light that was absorbed is the wavelength that gets emitted.
Let's say this again. Because of the structure of elements in a gas, cold gases absorb certain wavelengths. That's where the black lines come from. When that same element gets hot enough to emit its own light, the wavelengths it emits are the same ones that got absorbed when the gas was cold. That's why emission spectra have the bright lines.
Why is this so important? Well, everything that emits light has an emission spectrum and an absorption spectrum. We can use a special telescope to look at an object's spectrum and track its emission or absorption lines. That means if we know the emission and absorption spectra of all the elements and molecules, we can compare the spectra, and then we can determine the chemical composition of everything we can see. Neat, huh?
By using emission and absorption spectra, we can figure out the chemical compositions of stars and planets and all kinds of other things.
But figuring out chemical compositions isn't the only way astronomers use light. They can use light to figure out whether objects are moving closer or further away from us.
Section G. Doppler effect.
A good way to demonstrate the Doppler effect is with boats in water. When the boat isn't moving, waves just lap off it in perfect circles. When the boat starts moving, waves move with it as it goes. See how they pile up on the front side and stretch out in the back?
Yeah!
Same thing happens with light. Before we can explain why, you have to remember that blue light has a short wavelength and red light has a long wavelength.
Blue light short, red light long. Okay.
When waves of light get emitted, they all move outward at the same exact speed. If their source moves, then the waves tend to pile up in the direction the source is moving and stretch out in the opposite direction. This piling up and stretching out changes the observed wavelengths.
Light sources that move toward you look bluer than they really are because their wavelengths are piling together and appear to be getting shorter. We call this blue shifting. Blue shifting means the light source is moving toward you.
By the same token, light sources that are moving away from you look redder than they actually are. As the light source moves, the wavelengths stretch out and look redder. This is called red shifting. Red shifting means the light is moving away from you.
Astronomers can do different calculations to figure out how fast the light source is moving away from or towards us. Don't worry, you won't have to do the calculations yourself, but you do need to understand the implications of blue and red shifting.
Oh yeah, one more thing. Blue and red shifting usually isn't noticeable unless the light source is moving really fast. Otherwise, the shift isn't big enough to see. That's why headlights of oncoming cars don't look blue.
Speaking of seeing, let's talk about how we see everybody else. My right eye during astronaut training was put out by the tip of one of them rocket ships.
Part 5. Telescopes. How we see everybody else.
Galileo is credited with creating the first telescope. Galileo's telescope is called a refracting telescope because the light entering the telescope is refracted or bent by a lens at the top of the telescope and focused on another lens at the bottom of the telescope.
Refracting telescopes are okay, but to get better images, you need bigger lenses. Bigger lenses are harder to craft without mucking them up. And the other problem with big, thick lenses is that they start acting like prisms and break up the light into a spectrum. That makes it harder to see the stars you're trying to look at.
Isaac Newton invented the kind of telescope that most astronomers use today. This kind of telescope is called a reflecting telescope. In a reflecting telescope, light enters the top of the telescope and bounces off a curved mirror on the bottom of the telescope. The curved mirror focuses light on another flat mirror, here in the middle, which reflects the image to an eyepiece on the side of the telescope. Almost all modern optical telescopes are a variation of the Newtonian model.
The reflecting telescope is also better because it can be made bigger. A glass lens can only be about 1 meter in diameter before it gets messed up, but the mirror of a reflecting telescope can be 4 meters wide, or wider.
With telescopes, the wider you make them, the better resolution you get. Scientists don't care so much about the magnifying power of a telescope. They want their images to be clear. That's what resolution does.
Here's an example. Magnifying glass, magnifies. Eyeglasses, resolve. Driving with magnifying glass, driving with glasses. You get the idea.
But optical telescopes aren't the only kind astronomers use. They're telescopes to detect radio waves, gamma waves, microwaves, ultraviolet light. Heck, we're checking out the sky in every part of the spectrum. The thing is, how big your telescope needs to be for good resolution depends on the length of the wave you're trying to catch. Gamma ray detectors can be pretty small because the waves they detect are so small. Radio waves are so big. Radio telescopes can be huge.
The biggest radio telescope is a thing called an interferometer, which has a bunch of radio telescopes working together to simulate one big one. This makes the interferometer's effective diameter span continents and gives the interferometer very fine resolution.
Astronomers describe the resolution of their telescopes in terms of arc minutes and arc seconds. Arc minutes and seconds are units of angular measurement, which is a way of measuring pieces of circles.
There are 360 arc degrees in a circle. A degree is made up of 60 arc minutes. An arc minute has 60 arc seconds.
The resolution measurement of a telescope is how close together two objects can get before the telescope begins to see them as one big blob. The best telescopes we have now can achieve a resolution of about 0.5 arc seconds. That's pretty small. Radio interferometers and the Hubble Space Telescope can see resolutions that small. Let's do something fun.